Dear all, welcome to this new episode of the CATIA TV, this time on a very strategic topic of CATIA Stiffeners. The idea is to create, validate, and quickly converge concept-stiffened structures using CATIA. The stiffened structures concept design engineer role empowers the engineer with modeling and simulation capabilities in order to boost the convergence of conceptual and preliminary design studies that are driven by their targeted structural properties. Stiffened Structures Concept App delivers all the necessary tools to create a conceptual model, from the assignment of composite laminate onto regions, the creation of the finite elements model fully capturing the design specifications, and the setup of structural simulations, loads, and boundary conditions to the solving of the simulation. All these tools are available on the same app, enabling the engineer to focus on the workflow by eliminating the need to switch from modeling apps to structural simulation apps. Our subject matter expert, Nicolas Guérin, will expose the latest updates from the role. As usual, the CATIA TV webinar will be held here in the post where you are right now in our CATIA user community, and it will give you the capacity to interact in live with our subject matter experts throughout the chat. So don't hesitate to rewatch the webinar, and we wish you a very good day.
Hello everyone, and welcome to this CATIA TV session. My name is Nicolas Guérin. I'm part of the CATIA R&D roles portfolio management team, and I'm very happy today to present you a new role and a new app we have dedicated to a stiffened structure and the engineering of this at the concept preliminary design stages. So, without further ado, what is a stiffened structure and what's the engineering of it? So stiffened structure, you have plenty of examples. It's anytime you have a skin or a panel where you would want to control the thickness of it or see what would be a good trade-off between a thin skin and underlying structure made out of stiffeners like stringer, ribs, frames. You can find plenty of examples of that in the aerospace industry, as well as marine and offshore and industrial equipment. So basically here, the goal of this tool is to find the best balance between the shape, the external shape you need to respect, and what could be the way to reinforce this structure by playing on the materials, playing on the thicknesses, and the stiffeners properties. So typically, like for a wind turbine blade or for the skin of an airplane, the wing of an airplane, you would have a shape coming from CFD or any other input, and structural engineer would have to find the best way to stiffen this part to sustain the structural loads. And this tool is really here to help you converge quickly on a good compromise in terms of thickness materials and stiffening structure to achieve your goals. Here is a quick video that would illustrate what I've just said. So here we have a new wing that's been determined through CFD, and the structural engineer is asked to find the best way to stiffen it. So we go into the app and we start defining on the upper skin here some cells. As you can see, it goes really fast. That's what we call the quick grid to create cells on your surface where you assign some materials and thicknesses. So in this case here, it's composite materials, and we have predefined laminates. I'll go more in details into that later. And you start doing a first assessment, hypothesis, I would say, of the material distribution on your surface. You have a finite element model that's built upon this definition right away, taking into account for the section properties directly what you've input on your geometry. So it goes super fast, and you can assess that you have actually for each finite element the proper stacking of plies with each orientation displayed here, the stiffness matrix computed, and you even have a view of the thickness to make sure that you've input what you actually wanted to do. Once you have that, you can input it into a bigger finite element analysis. Here you utilize some pressure that you got from your CFD computation, and you assign it to your structural element to perform a finite element analysis and assess here in this case the displacement or whatever KPI you may be interested in. So in a nutshell, this role is here to really boost the convergence of your structure at the very early stages of conceptual or preliminary design, targeting, of course, the structural behavior of your part. One of the key points is, of course, to offer here through the Stephen Structure Concept app, what we call an all-in-one app, where you would have all your modeling and simulation, ModSim, capabilities all packed in one application. So the goal, of course, is to boost the exploration of your design, to find quickly the best compromise, including, of course, capabilities, as you'll see, to reduce your model, like the structure we saw earlier can be turned into just beam elements for much faster simulation and therefore faster convergence of your properties. It's fully compatible with the CATIA and Simulia portfolio in terms of geometry, modeling, and also simulation. And it's a good tool basically to go anywhere from a concept phase to the detail phase, working on the same model. So I'll go a bit more in detail now into the phases of this role with this little workflow you can see on the screen right now, where we would start from just a surface. We'll define a bit more the various laminates we can put. We'll assign them with a quick grid to the surface. Also position the stiffeners and the structures, and then go into the finite element world to define the loading it has to sustain, and then converge. At any point, of course, as it's all in the platform and integrated, we can of course come back and change whatever parameters in our setup to go further. So let's go more in detail. So it starts with material parameters. So those of you familiar with composite design would find a familiar face here. It looks a bit the same, but it's not called composite because the ambition with this role is to actually offer something more generic. Composite as well as isotropic, like metal, could be also put in the long run. For the first release that we have, it's still focusing just on composite. And we introduce here some laminates, and I want to show you here the thickness ratio one. That's a very interesting one. It's brand new. We define for each material a ratio of the various orientation. Of course, it has to add up to 100%. And you define a target thickness. And that's going to be really useful, you'll see, to converge quickly what would be your ideal structure. Now we go into the quick grid, and we have put in this capacity ways to define on the fly some structural elements to put the boundaries of the cells. or you can, of course, reuse existing geometries to intersect this surface or project onto this surface if you already have these elements. So you have the best of the two worlds. You define on the fly something to go quickly without bothering too much about the creation of the geometry, or you reuse whatever exists already in your design that you see fit. And then after you start playing by putting, and you can of course multi-select either on the quick grid panel you see on the right hand side, or directly on the 3D. You select the cells and you assign some existing laminate you've defined just earlier to start your hypothesis, putting a thick area where you think it needs to be there, and making something a bit lighter wherever you think it can be lightened. So you have, of course, ways to display some information at that stage, like the overall thickness, the number of plies you have, to make sure that whatever you've input actually makes sense at that stage. And of course, you can revise if need be. So what you see here is really real-time demonstration, and it's not called quick grid for nothing, as you can see. And if you're used to the composite grid that has been in the composite design roles for quite a while, you would find it very similar, but actually much faster. So of course, numerical analysis is available here also to assess that you've adequately defined everything on your surface. At that stage, well, it's time to go into the finite element modeling. It's going to be fairly transparent. You create a mesh by putting as a support for your mesh your grid, basically, and constraining by the elements of the structural elements you've used in your quick grid definition to make sure your elements are well constrained by these borders. So here in this tool, we have utilized the standard finite element capabilities offered by the Simulia roles. So those of you familiar with it should be up and running very quickly with this tool. So here we capture the various constraints of the FEM and making sure that we get a satisfactory FEM in the end. So here I keep on going with the demonstration so that you can keep this as a reference whenever you want to play with the tool. Here you can notice that on the tip here, with the mesh size we have taken, some simplification is done automatically, so that you can go ahead and edit and make sure you want to not simplify your geometry and make sure you have elements going everywhere. Once you're happy with your finite element model, here just make sure to go and perform automatically a core sample of the composite material at each position of each element directly using the grid information. Once again, fairly transparent. We'll go now into the dedicated tool to display the computed sections to make sure the translation between the grid into the section properties is just all right. Once again, relying on standard Simulia capabilities for the visualization of the finite element properties with composite materials. In particular, the ply stack plot viewer, very useful tool where you see for each element a representation symbolized of the stacking with the various orientation and materials if you were to put several materials and of course the global thickness. Once again, this is just a basic checkup to make sure you've correctly defined your material. But then again, you don't have to go through all this phase at each point. But it's just to illustrate. So here we use the thickness ratio, and you can note that actually many plies are connected with the same orientation. That's all natural actually, because thickness ratio at that stage we just don't care really about the sequence of plies. So when we define that there is like 10 plies basically in like zero orientation, then they are all on top of each other. So for sure at that stage, we are going to perform some structural simulation where the order of the plies does not really matter. If it was to matter, we would use a different way to define this laminate. That would be the stacking sequence, which in this case, the order of the plies is really useful. And for stacking sequence, we have capability, of course, to export and import existing laminates, ordered laminates that could be in an Excel spreadsheet format, for instance. So still going on with the display, we are going to look at the global thickness of the finite element with a thick representation and a factor to actually highlight the differences. Once again, making sure that what you've input is correctly interpreted at all stages. But then again, once you're confident in your model, you don't have to go through these phases, and you can just jump into the structural analysis right on. So, as again, like if you were to change something at that stage or later, if you think you need to put some reinforcement, just go back to your grid, and on the fly you can just add some more structural elements, like we'll see. So directly, automatically, it creates some new cells, manages the numbering and all that. And on these selections of cells here, we are going to put a different laminate to reinforce this section. There you go. Your grid is updated. And by the way you have defined your finite element modeling, everything is associative at that stage. You just need to just go ahead and update, and your reinforcement is taken into account right away. There we go. So at that stage, we'll just go ahead and go on with our finite element analysis. So, of course, checking that, once again, that it correctly has taken into account the reinforcement. There you go. You see the reinforcement as we have just defined it in the grid. All right. Now we keep on with our structural simulation. We are going to put typically boundary conditions and loads onto our FEM. We simplify a bit the view so that it's easier to handle. Static perturbation step. So it's good to know that with this role, we're offering some linear capabilities for structural simulation. We are not going into the full-blown non-linear capacities that Simulia could offer. We stick just to static perturbation. We offer also 4 CPU of embedded compute capacity, so you don't need to really to go purchase additional simulation tokens or credits to run a simulation, as long as it sticks with 4 CPU, which should be fine for this type of simulation and model size. So we'll see here that you can just specify that you would perform your simulation with your embedded capacity that's come with a role, and run your simulation, and then you will be able to display the results of it. And of course, directly see the effect of the hypothesis you've made on your material distribution on your surface. So here we have the displacement, typical post-processing capacities that comes naturally with a simulation. You can also look, of course, at stress, like as it is a composite material, it's good not to perform a von Mises that tends to hide what's going on in the various directions. And if we wanted to have some composite-specific post-processing output, we need to request it actually before launching the simulation, because it's not by default one that's going to be computed in your simulation. But you can ask here to output some composite-specific criteria, such as Tsai-Hill, Tsai-Wu, and other failure criteria that the Abacus solver offers. So unfortunately, if you have not thought of that earlier, you need to just relaunch your simulation so that this output will actually be computed and stored with your simulation results. There you go. And at that stage, well, I would say now you can play. You can see your Tsai-Hill criterion is fairly low. So obviously, with this loading, probably you can optimize your structure and probably shred some weight. So I've just illustrated that. We didn't spend too much time into the internal stiffener. At that stage, it's going to be mostly handled through the finite element analysis. You can put on your structural elements that you've defined with the quick grid some beam properties directly input in the FEM. Later on, with this role, we are going to offer also much more capabilities to define your stiffeners and create underlying geometries much more refined for them. So once again, this is a fairly young tool, and also another big area where we want to go, as I said, is to offer not just for composite materials, but what we will call the generic grid that can address also isotropic materials like metals. So now that we've spent quite some time on the what we do on shells, I want to introduce a different workflow. Start the same 1, 2, 3, 4, but then we are going to reduce the model and go into what we see on the top of the screen, where we are going to reduce our model actually into a 1D beam, if it makes sense. Of course, if the structure is one where it would make sense to reduce it to a 1D beam. So I'll show you that in a bit more detail, how we reduce into an equivalent beam that, of course, would be much faster to solve, and then to converge, we would go back to our definition on the 2D, and that should speed up very much the process. So here, typically, we think that like a wind blade could be a good example. So we have various grids here in the upper, lower, external surface, as well as the stiffener, the main stiffener inside the blade. We'll use this yellow center line to be the support of the 1D beam element that would represent the entire wind blade. And we calculate for each of these various sections the equivalent inertia properties it has based on the grids, the various grids we have. We then apply some loads and boundary conditions onto this beam and solve it. And of course, it goes much faster because you have way less degrees of freedom in your finite element model. But for some KPIs like the max displacement here, this gives you a fairly good indication as to how your overall blade behaves, and you can therefore quickly converge your properties and go much faster into refining something that's going to be a very good candidate for your structure. One thing I want to mention also with this role, because once you've set up all of this, as you can see, it's all connected in the platform, and now you can play. Everything is open as knowledge parameters. So we have put in the packaging of this role parametric design study, an app coming from Simulia that offers a great capacity for design exploration. So once your model is well parameterized, and here we are showing how you can play with structural element position, as well as playing with the target thickness of the thickness ratio laminate that we've seen earlier. We have put in a design table some predefined type of laminates, making sure the ratio always adds up to 100%. And we can shuffle all of that now into basically a design of experiment where we are going to give a range for each of these parameters and see how this model behaves when we play with some of these key parameters. So it's all integrated in the platform. No need to go anywhere. It's all the exposed parameters are accessible, and here we have what we call the design space check. So for each point of the design of experiment, where we vary some of the parameters, we make sure the update of the model goes well, and that is ready to go into further studies. So that's where we say now we can play, because once it's all well defined like that, then you can really explore and perform some sizing into your structure to go assess if it's a good candidate for your structure. So for instance, you can put as an output, for instance, of your finite element you would put on this model that I've just shown here. You can ask to output the global mass to see how it evolves. You can also have some sensors for buckling or a Tsai-Hill criterion to make sure at each point that it's satisfactory. So I want to say one word also of where this role would fit in our existing fairly comprehensive portfolio, especially on the composite end-to-end solution. So you would see a position on this spiral here, the various stages where we have solutions from various brands to come and position. So of course, this one here is a good fit to start your engineering process with concept design, preliminary design, where the structural behavior is really the driver for your sizing. The good thing is, the quick grid, whatever you've put there, is fully compatible with the grid in composite design. So at that stage, there is not even data translation. Once you're happy with what you've come up as an hypothesis of your design with Stephen Structural Engineer, the model can just be given to a composite designer for detailed design, taking into account more design rules, but there is no loss of data. It's fully compatible. It's also fully compatible with the rest of the Simulia portfolio. So if you need to go into more nonlinear simulation to study more precisely some behavior, you can do so also directly from the modeling you've done in this tool. In terms of packaging, in 2X GA, this role, Stephen Structural Engineer from CATIA, would be put in two IPEs, industry process experiences, for aerospace and defense. In aerospace structural engineering, that belongs to co-design to target industry solution experience, and in aerospace concept structural engineering, that belongs to the winning concept industry solution experience. You'll find it also in the marine and offshore boat composite industry process experience, and in industrial equipment in the composite parts engineering industry process experience. That's for the beginning. That's to cover also the main industries where we see great value with this role. To conclude, the key takeaways I want you to have with this tool, the new CATIA role, that's going to be of general availability in R2023X. It offers one key app, that's Stephen Structure Concept app. That's an all-in-one mode sim application that offers also 4 CPUs of embedded computation. It's fully scalable and compatible with CATIA and Simulia portfolio, even though it comes already with nice features from both brands, actually, like generative shape design and linear structural simulation with the Abacus solver. Right now, the focus is on composite. But of course, we won't stop there. There is no composite in the name. It's really for a generic grid that would allow you to find the best compromise, including what would be the best material and the best thickness you can find for your material. And we'll go also into a much more refined definition of the stiffeners as we go on. And it's available on premise and on the cloud. And for early adopters, it's also available in the 22X portfolio, fully maintained, documented, and supported. So that's about it for today. I'm very happy to have have presented you, to have introduced to you this new tool. We are very excited about it, and we are also very excited to see where it's heading. And thank you for attending this session of CATIA TV in the heart of summer. And I look forward to your question and discussing this more with you. Thank you.